Bismillahirrahmanirrahim. Let's start with chapter 4 movements. Okay, so before starting movements as a chapter, I think it is very important to understand because movement is made up of two variables. One variable, if you define movement, is product of force into distance. So, how is a movement generated? It is generated because of uh, the force. It is being generated because of the force, and we all know that what is a force basically. So that is a very basic question. So all engineering design calculations are always use Newtonian mechanics. In classical mechanics, what do you mean Newtonian mechanics? It means it's mechanics based on the three fundamental laws of Newton. Newton's first law of motion, Newton's second law, and the Newton's third law, which was being explained by me in our very first fundamental lecture. So in classical mechanics, the concept of force is based on experimental observations that everything in the universe seems to have preferred configuration. Like masses appears to attract each other. Which law? Newton's law of universal gravitation. You all always heard about it. You have done some calculations on it also in your metric and inter exams. Objects with opposite charges attracts each other. Magnets can repel or attract one another. You are probably repelled by your professor. I don't know. I think you are good students. It's not like that. But we don't really know why this happens, except perhaps the last one. The idea of a force is introduced to quantify the tendency of objects to move towards their preferred configuration. If object accelerates very quickly towards the configuration, then we say there that a force is very big, the magnitude of force is very high. If they don't or moves at some constant velocity, then the force is then there is either no force. We can't see a force. We can only deduce its existence by observing it. Okay. So definition of a force. Force are defined through Newton's law of motion. Some very important definitions already explained to you. Particle, the small mass at some position in space. When sum of the forces acting on a particle is zero, its velocity is a constant. The sum of forces acting on a particle of constant mass is equal to the product of mass of the particle and its acceleration. What is this actually? It is F is equals to ma. What is this basically? It is summation of all the forces equal to 0, and the forces exerted by two particles on each other are equal in magnitude and opposite in direction. What is this? This is Newton's third law of motion. So if you want to define and ask you a force, there are many definitions, simple definitions you have heard, but force is best explained by virtue of these three laws of motion. Newton's first law, the second law, and third law, if you wanted to explain force. The second law provides the definition of a force. If a mass m has an acceleration a, the force will be F will be equals to ma. There is a big problem with Newton's law. What do we take as a fixed point and orientation in order to define acceleration, which means our coordinate axis, what will be that you need to define. That you will basically discuss on the basis of the theory of relativity addresses this issue very much vigorously. But for engineering calculations, we usually take the earth to be fixed and happily apply Newton's law. Okay. In rare cases, when the earth's motion is important, we take the star from the solar system to be fixed. That is when we are talking about heavenly body systems in space. Then very important, how is basically this force is being generated. we will call it the causes of the force. Force may arise from a number of different effects, including, again, you can clearly see you can generate force by means of gravity, electromagnetism, or electrostatics, pressure exerted by fluid or gas in parts of a structure. You know, kinetic theory postulates, remember, it basically belongs to that. If you focus it, wind or fluids induced drag or lift forces. Then very important forces I have discussed in mechanics that will come a lot in statics and dynamics, and that will be the contact forces, which acts wherever a structure or component touches anything. Okay, whenever two components are basically in touching each other, it will generate a contact. It can be, for example, two gears lying on each other, or your feet on the earth is basically a contact. So there are numerous examples of contact forces, and this contact forces we will be dealing a lot in our course of engineering mechanics branches, statics and dynamics. So contact forces. Then another very important and a very weird force that will come, and we will also study it, a very important not only in statics, but this force is also very important in dynamics. It is called as the friction force, which is also a contact force, but this force, how it always opposes the motion. Wherever a motion is generated, this force will come and it will oppose its motion. And remember, when you will study this force, you will see that this force, when it opposes the motion, it can be a blessing for humans. It can be a blessing for us when we are driving. It can be a blessing for us when we are running on a slippery surface. You can understand why. Because if there is no friction on a smooth surface, what will happen? You know it very well. Okay. So some of these forces can be described by universal laws. For example, the gravity force can be calculated using Newton's law of gravitation. Electrostatic forces acting between the charged particles are governed by the Coulomb's law. The electromagnetic forces acting between the current particles wise are governed by the Ampere laws. Then there are buoyant forces. Okay, buoyant force is basically equals to the weight. Opposite are governed by laws describing the hydrostatic forces in the fluid. Some of these universal forces are listed in section 2.c. You can see it yourself. Okay. Some forces have to be measured. For example, to determine the friction forces acting in a machine, you need to measure in order to find friction, what you need to measure very carefully, it is the coefficient of friction, and it will be different for every surface. For steel it will be different, for iron it will be different, for aluminium, for copper, for brass, for sand, it will all be, coefficient of friction will be different. Okay. Similarly, to determine the aerodynamic lifts or drag forces acting on a structure, you would probably need to measure its lift and drag coefficients experimentally. You will be studying these things, lift and drags, when you go to your higher second year in specifically in your fluid mechanics courses and car body design if you are an automotive structure engineer. Okay, so lift and drag forces are described in section 2.6. okay, if you see it over here, it is coming. Contact forces, what are these? These are pressure forces that act on a small area of contact between two objects. Contact forces can either be measured or they can be calculated by analyzing forces and deformation in the system of interest. They are very complicated. So when we will study contact forces, I will basically make it sure for you that we study in the most simplest of the fashion, and we will not go in very complex equations, just to ease our calculation. Unit of force, the SI unit of force is Newton, and the Newton is a derived unit. Okay, so it's basically equals to 1 kg mass to accelerate, needed to by 1 kg mass to accelerate a distance of 1 meter per second square. What is its fundamental SI unit is kg meters per second square. kg stands for unit of mass, and meters per second square is a symbol of acceleration. Okay, let's go ahead. Okay, then another unit for one force of 1 pound for one force of 1 pound force causes a force of 1 pound force causes a mass of one slug to accelerate 1 feet per second square. How we define slug? Basically, W equals to mg, so m equals to w. But here W is not in Newton, it is pounds, and g is not in meters per second square, it is in feet per second square. Okay, and what is the value of g in feet per second square? 32.174 feet per second square. A force of 1 pound force causes a force mass of 1 pound mass to accelerate 32.1740 feet per second square. The conversion factors are 1 pound is equals to 4.448 Newton and 1 Newton is equals to, so if you have 1 pound force and I ask you to convert it in Newton, you just need to multiply it with 4.448 Newton. Okay, and the other way around is basically 0.2248 pounds. As a rough guide of force, 1 Newton is about to equal to the weight of a medium-sized apple. Okay, so here are some constants, and basically gravitational pull of the sun on the earth from Newton's law is basically 3.5 into 10 to 22, and pound force is 7.9 into 10 to the power 21 Newton pounds force. Okay, very important topic coming from dynamics point of view as well, and statics. Classification of forces. So external forces can be, there are basically external forces, constraint forces and internal forces. So if I say to classify those forces, we will always say the force can be external nature, or a force can be internal nature, or there is another category of classification of forces, that is constraint forces. So when analyzing forces in a structure or machine, it is conventional to classify force as external force, constraint force, or the internal forces. Now you will be interested in what is an external force. External force arises from the interaction between the system of interest and its surroundings. Okay, so any system of interest that you are undertaking and there are some forces acting, those forces can be acting because of anything, because of some motor being placed over there, or some vibrational effects are being there, or something falling down. So these on any system as a result of gravity, so all these forces will be termed as the external forces and the interaction between the system of interest and its surroundings. So example of internal forces includes the gravitational force. As I told you before, gravitational force is basically an external force. The lift or drag forces, can you tell me where this lift and drag forces comes? If you just put some pressure on your mind, you will see that this lift and drag forces plays a very important role when you are speeding your vehicle on a motorway. So basically drags comes, and drag force is very important. And when you are in an aeroplane, over there the forces of lift or drag is very critical, and they need to be properly balanced so that the aeroplane might fly. If there is a non-balance, if they are not being balanced, so the lift and drag forces, then the aeroplane will not be able to fly in the sky. Okay, so you will study this in your second year. So electrostatic forces, electromagnetic forces, and the buoyancy forces, among others. Forces laws governing these effects are listed in the section you will study. Okay. Then there are also constraint forces, very important, and our chapter 4 when we end, when we go to chapter 5, these forces we will study a lot in our chapter 5, chapter 6, chapter 8, and to some extent in chapter 9 of gravity, center of gravity and centroids of objects. So what are the constraint forces? The constraint forces are exerted by one part of a structure on another through joints connections or contacts between the components. So you can see these joints and connections or contacts. These joints, if you go to a bridge has been connected by means of joints, then there are various connections in beams by various supports, and there are contacts between various components. So constraint forces, they are very complex. Then the third one, very important force, and it is the internal force. Internal forces are forces that act inside a solid part of a structure. They will never act on the external part. Why? Because for the external part we have the force which is named as external forces. But internal forces are forces that act inside a solid part of a structure or component. For example, a stretch rope has a tension force acting inside it. As I explained you in the various numericals, remember in the week 1 numericals that we did, and week 2 also, there will be stretch ropes, or we have what is called as cables. They always undergo, whenever say we understand we have a force analysis on these cables or ropes, we will always assume when a force is acting, it will be a tension force acting, holding the rope together. So most solid objects contains very complex distribution of internal forces. These internal forces ultimately lead to structural failure. Okay, so when we say a structure fails, a bridge collapses, or a house collapses, or basically some sort of a structure undergoes catastrophe, then that basically is basically there is some sort of an accident undergoing. A car crashes on a wall, a two-car undergoes a crash, frontal crash, or a side crash. So basically it will lead to a structural failure and also causes the structure to deform. Okay, so the purpose of calculating forces in a structure or component is usually to reduce those internal forces. Okay, so very important. We will not unfortunately be able to develop full theory of internal forces in this course, because we are basically studying, remember, we are basically studying rigid body systems in statics, and so we assume that our body will not deform, but internally, I told you there is no body in the world which is rigid, all body deforms. So there will be external forces in a body and there will be internal forces in the body. Okay. So these internal forces, whenever we study, we will be discussing it in slender members. Okay, slender are basically thin walled structures. Now we go to another very important topic, which you have be already knowing it, because we are actually, remember, we are doing this course, but at the background, this thing will basically be implemented in movement, and movement's critical component, I am repeating once again, is only generated if a force is there. So if there is no force, there will be no movement. Mathematical representation of a force. Force is a vector. It has magnitude specified in newtons or pound force and a direction. Okay, so here you can see there is a force not shown, but its three respective components are given. The force along x-axis is fx, and the force along y-axis is fy, and the force along z-axis is fz, and its three unit vectors will be, remember I told you, force along fx will have fxi, fy will have fyj, and fz will have fzk. A force is therefore always expressed mathematically as a vector quantity. Okay, the force is expressed mathematically as a vector quantity. To do so, we follow the usual rules which are described in more detail in this vector tutorial. Okay, the procedure is very simple. Choose the basis vector. Always choose the basis vector. And what are the basis vectors? As always you have studied, I, j, k are the basis vectors. They can always they can also be shown as E1, E2, E3 in some books. They will still be called as the unit vectors or the basis vector. That establish three fixed and usually perpendicular direction in space. Okay, so what are the three fixed? Origin, I, J and K, and this is all what is basically occurring in space. Why space? Because three dimensions are always in the space. Okay, let's go ahead and remember this. I, Fx, Fy and Fz can always be expressed as equal to, the resultant force will be equal to Fx plus Fy plus Fz equals to F. Number 2, using geometry or trigonometry, calculate the force components along each of the three reference directions. And what it is, Fx, Fy, Fz, if your axes are x, y and z, or you can also say if your axes were E1, E2, E3, so your force components will be F1 acting along E1, F2 acting along E2 and F3 acting along E3. The vector force is then reported as F is equals to Fxi plus Fyj plus Fzk. Okay, or you can also say it Fx will be as F1 and I will be as E1 plus F2 E2 plus F3 E3 in terms of appropriate units. So for calculation, you will also need to specify the points where the force acts on your system or structure. To do this, you need to report the position vector of a point where the force acts on the structure. Okay. So the procedure for representing the position vector is described here. Choose an origin, choose the basis vector I, J, K or E1, E2, E3 that establishes the three fixed directions in space. Specify the distance you need to travel along each directions to get from the origin to the point of application of force by Rx, Ry, Rz or R1, R2, R3 depending upon your axis or the coordinate system that you have taken. Okay. The position vector is then reported as R is equals to Rxi plus Ryj plus Rzk, or it can also be equal to R1 E1 plus R2 E2 R3 plus R3 E3. Okay. Then we go ahead, measuring forces. Very important. How do you measure force in the real world system? Okay. So engineers often needs to measure the force. Everywhere, whenever you go, the most important thing is that how do you measure this force? So from the definition, if we want to measure a force, we need to get a hold of 1 kg mass, have the force act on it somehow, and then measure the acceleration of the mass. The magnitude of this acceleration tells us the magnitude of the force. The direction of motion of the mass tells us the direction of the force. Fortunately, there are easier ways to measure force. Again, this whole logic is very difficult for us in the real world scenario. Okay. So in addition, the calculation accelerate the causing acceleration force causes objects to deform. The force will stretch or compress a spring or bend a beam. So deformations can be measured and are to be calculated. The simplest application of this phenomena, which we discussed on the top, is basically a spring balance, or it is called as a spring scale. The change in the length of the spring, which is delta, is proportional to the magnitude of the force causing it to stretch. This relationship, is also called as the Hooke's law, which is F is equals to K times delta. It is the Hooke's law. How much force is acting downwards, it will basically deforms the spring depending upon the magnitude of the force. Lesser the force, there will be deformation less in the spring. Higher the magnitude of force, there will be more deformations in the spring. When the spring stiffness K depends upon the material, the spring is then made from and shape of the spring. Okay, so it is basically being done by means of a spring balance. Spring scales are not exactly precise, okay, so sometimes you need to have more precise equipments, and for that what you do, you use basically devices called as force transducers, okay. They are basically also called as the load cells. Works much like a spring scale, but they are more accurate and more sophisticated. So in real world scenarios in automotive industry, or where you need to calculate force very accurately, you will be using load cells are force transducers. You can see in the picture below here, simple force transducer capable of measuring a single force component along its axis Fx, Fy or Fz. So very knowledgeable and very informative information over here, okay. A sophisticated force transducer produced by an MTS system is capable of measuring force and moments acting on a car's wheel in situ, as shown. The specs can be downloaded from this information. This is not important. Just see how they can do it over there. You can see there is basically a moment measuring device and a force measuring device is being placed to measure the forces and consequently the moments. Okay. So as an engineer, you may need to purchase load cells to measure force. So if you are working in a lab as an engineer, or you're basically doing some sort of research, so you need to buy, if you need to measure force, so you need to buy this device which is called as the load cell, okay, or which is also called as sometimes force transducers, okay. It works on this principle. You can read it, but it's not that important for you. What is important is to measure how you name the devices which are used to measure force. The crude device, not accurate, is spring balance, and the most precise one are the force transducers or the load cells. Then you go to another topic over here which is called as the force laws. We listen to the we list equations that can be used to calculate forces associated with these laws. The gravity forces, the forces acted by linear springs, the electrostatic forces, the electromagnetic forces, the hydrostatic forces, the aerodynamic and hydrodynamic lift and drag forces. So gravitational force is shown over here. It is very simple. You can see it is the law is the Newton's law of universal gravitation. F is equal to g m1 m2 over d square. And then since force needs to have a direction, it is being given by a unit vector E12. Then force exerted by the spring, very important, okay, just to understand the basic concepts of this. Solid object can be made to exert force by stretching it. The force exerted by a solid that is subjected to a given deformation depends on the shape of the component, the material it is made up of, and how it is connected to its surroundings. Solid objects can also exert, remember, not only forces, but they can also exert movements, and you can also exert torques, okay. So there are mathematically moment and torque are same, but physically, if you being an engineer, you are being asked, you will never say moments and torque are same. They are very much different, and I will tell you in our different exam in the coming classes how moments and torque are different. I usually ask this question also in the exam also, so just remember this. Forces exerted by solid components in a machine or structures are complicated. We'll discuss it later, okay. So here is an example. A spring scale is a good example of a linear spring, okay. This is an unstretched scenario. This is a stretched scenario. Force exerted by the spring, and you see this force F is acting downwards, this is acting upwards, and the force acting on the spring, and afterwards the system has to be in equilibrium. The two forces has to balance it out. This force will cancel out its effects of this force, and the system will be in equilibrium. If you apply the summation force along the y-axis, you will see that it will be in equilibrium. The force exerted by the end of the spring always acts along the line of the spring, and it will be equals to F equals to K into L minus A, and its unit will be Newton per meter or pound per feet. Electrostatic forces, very important being engineers, okay. Here, depending upon the charges, okay, Q1 charge, Q2, the distance between them, and then Coulomb law explains it more in detail. Yeah, Coulomb's law. Being since we are doing statics, we won't be going to the electrical effects, electrostatic effects of that. Okay. But you can read it for your knowledge point of view. Then hydrostatic and buoyancy forces. When the object is immersed in a stationary fluid, its surface is subjected to a pressure. The pressure is actually induced in the fluid by gravity, and the pressure at any depth is effectively supporting the weight of the fluid about the depth. Okay, here it is. There is a body, and this is the hydrostatic pressure which is being generated. Why it is low? Because the height is very low, and as you go, the height increases, and the effect of the pressure is being increased. The aerodynamic lift and drag forces. Engineers who design large bridges, buildings, or fast moving vehicles spend much time and effects in managing aerodynamic and hydrodynamic effect of forces. So hydrodynamic forces are also great interest to engineers who design bearings. Okay, bearings you will see very important in any rotating equipment, in your cars, in your wheels. If you are giving weird noises, sometimes your bearing is not being properly aligned, or it has failed. In car tires, hydrodynamic forces can also cause one surface to float above one another, so reducing friction to very low levels. This is an example of your wing. Okay, it's called as a wing, is also called as an aerofoil. So flow is asymmetrical near the aerofoil. A drag force acts parallel to the direction of the air or fluid flow. A lift force acts perpendicular to the direction of the air or fluid flow. Here is the lift coming from the downside. The force acts at a point known as the center of the lift of the object, but there is no simple way to project where the point is. Then two effects contributes to drags. The frictional forces, we will not study this because we will go and study in chapter 8 friction when it will come. Okay, you can read this for knowledge, but not in detail. Okay, just leave these graphs, they are not important because they are more elaborate, so we will not be studying this. Okay, now after gaining a lot of quite detailed information about the force and effects, its causes, its direction, its orientation, and how to measure the force, we are in a very better position now, in a much more better position to understand movement. And I told you movement is basically generated as a result of force. If there is no force, or the magnitude of force is 0, there will be no movement. Okay, so we go to this topic, movement of a force. The movement of a force. The movement of a force is a measure of its tendency to rotate an object about some point. Okay, so any point, any fixed point about which the rotation will take place, that point is very important. The physical significance of movement will be discussed later. Okay, so we will discuss by stating the mathematical definition of the moment of the force about a point. Okay, so if you look at it over here, this is your coordinate system I and J. This is your force F, which is at a some finite distance from this coordinate system. It is one point over here and another point is over here. So how we can reach up to this point to create this R? So one thing is that we need to have a coordinates of this point, and we take the coordinates of this point where the force F is originating, and we take the position vector R. Another way, we have another point A. So we take the coordinates of this point and take a position vector as RA, and this is R. Now in order, this is point A, and this, to reach point this, we can say, if we say R minus RA, it will be what we will reach over here, and this position vector will be called as R minus RA. Coordinates of this point minus the coordinates of this point will give you R minus RA. Okay, you understand that? We go ahead. Definition of the moment of a force. To calculate the moment of a force about some point, we need the following three things. Okay, the force vector expressed as components in a basis fx, fy, fz are f1, f2, f3. Previously I told you, are better as this force can be expressed as a resultant as f, which is equal to fxi plus fyj plus fzk. Okay, so this is, remember I told you in the previous slide that those three components, when we were discussing, could be expressed as fxi plus fyj plus fzk. Okay, the position vector relative to some convenient origin of the point where the force is acting are better. It will be, I told you, the position vector R is equals to xi plus yj if you have a two-dimensional system. If you have a three-dimensional system, it will be xi plus yj plus zk. The position vector of the point, say point A, we wish to take moments about, you must use the same origin as for 2. So xa, ya, za are Ra is equals to xai plus yaj plus zk. Okay, so they are just trying to explain you over here. So the moment of F about point A is defined as M A is equals to R minus Ra cross F. Okay, R minus Ra cross of F. We can write out the formula of the components of MA in a longhand by using the definition of cross product. Okay, remember, moment is basically a product of F into D, but specifically speaking, it is the cross product of R and F. Okay, it is the cross product of RA. So if we have this vector, RA is x minus xa, y minus yaj, and z minus za, I, j, k are the unit vectors, and we cross it with F, and F is fxi plus fij plus fzk. And we can express, whenever we apply R cross F, we can take a determinant of it. So ijk, x minus xa, y minus ya, z minus za, and cross of fx, fy, and fz. So we solve this, we get this thing in terms of I, in terms of j, and in terms of k. So the moment of F about the origin is a bit simpler. Okay, so m naught is equals to R cross F, and they have simplified it in terms of components. M naught is equals to moment, naught stands for moment about the point O. It will be xi plus yj plus zk into cross of fxi plus fyj plus fzk. Okay, if it is about the origin. So when we say about the origin, so xa, ya, and za, they will all vanish out. It will be very simple. M naught equals to this determinant, and you simplify it, you will get equals to yfz minus zfyi plus zf curly bracket open zfx minus xfz j plus xfy minus yfxk. So simplify this and you will get this. Often the best way to find the moment of force about some point is simply to use the point of interest as origin. Then use the simple formula, this simple formula. Okay, resultant moment exerted by a force system. Okay, so if you have a resultant moment, if you want, you need to have those position vectors R1, R2 till n resultant position vectors Rn and F1, F2, F3, F4 till n points. So resultant moment of the force system is simply the sum of moments exerted by the forces. You can have infinite number of forces going to n point. Okay, you can calculate the resultant moment by calculating the moment of each force and then adding all the moments together. Okay, when you complete the resultant moment, you must take moments about the same point of every force. Again, this is a bit more theoretical, might be confusing to you, but again, just remember this: when we will solve the numericals, we will apply these concepts. Okay, and when practically we apply, we understand it much better in terms of practical numerical situation. Okay, so example of moment calculations using the vector formulas. Okay, so for example, we can work through few examples, but I'm because they are a bit more theoretical. If I guess, I will not be doing this. I will go for practical numericals. Okay, so just leave them to understand it a bit better. Another point comes physical significance of a moment. Okay, so this is important to understand theoretically. A force acting on a solid object has two effects. It tends to accelerate the object, making the object center of mass move, and number two, it tends to cause the object to rotate. So very important how to understand the physical significance of a movement. Okay, the movement of a force about some point quantifies its tendency to rotate an object about that point. Number one. Number two, the magnitude of the movement specifies the magnitude of the rotational force. The direction of the movement specifies the axis of rotation associated with the rotational force following the right hand rule convention. Like this is the force acting over here and it is the distance t. When this weight it is being fixed over here, now this weight W will be able to rotate this beam or this slide in a direction which is called as anti-clockwise. So a force is applied to a pivoted beam. Where is the pivot here? This is the pivot. Okay, and this is the direction. And if you look at this direction, this direction is an opposite direction compared to the direction of the clock. So we call it anti-clockwise. And the moment produced will change as the effect of this d change. It can be d by 2, d by 3, d by 4, 2d, 3d. Okay. So we will leave this because in the other theory we will be basically understanding it. So just consider what I am telling you. Like if you want to understand the direction of the movement, like you use the right hand rule. This is your, if you have this finger will be called as R, the other finger will be called as F, and this will be your movement. And if you curl about this R and F, you do a curl of your right hand, it will give you the direction about this thumb, which will be called as the R cross F. Okay. The direction of movement specifies the axis associated with the rotation force following the right hand rule convention. Okay. Okay, another topic, just understand a few tips on calculating moments. The safest way to calculate moment of a force is a slog through MA equals to R minus RA cross F, which means wherever there is forces acting and from the origin we want to understand of interest, take the position vector R minus RA. Okay. Here they are trying to say the previous example I told you before when we started the topic moments. Okay, the same thing is here. So we basically stop here and we go to another explanation because we understand the basics of movements. Now we go to the topic of couples, what are couples and how they are being generated. We go to another topic. Movement further extension is force couples, pure movements, couples and torque. So I just wanted to give you the definitions and bit of figures. Don't go into the complex calculations, just simple definitions and figures will tell you what is the difference between all of them, and we will go in depth numericals after this theory. Okay, we'll study the theory for a little bit more further, and when the numericals come, things will be more clear. Okay, so we have seen the force acting on a rigid body has two effects. Number one, it tends to move the body, and number two, it tends to rotate the body. This is the effect of force. If I ask, you will answer these two questions. A natural question arises: is there is a way to rotate a body without moving it, and is there is a kind of force that causes only rotation without translation? And you will be doing it this a lot. Let's see when it comes, and you are basically able to understand that. The answer to both question is this thing. What is it? It's the force couples. What is it? A system of forces that exerts a resultant moment but no resultant force is called a force couple. Very, very important. System of forces that exerts a resultant moment but no resultant force is called a force couple. And what is it? This is an example of a force couple. See, this force is F. This force is not F, it is minus F. What is common between them? They have the same magnitude, but what is different between them? This is acting on the positive, this is positive force, and this is negative force. So what we will do, as again the same logic, this is our origin. From here to here, we will take a position vector, coordinates of this point and coordinates of this point. It will be R, and from here to here we will take another position vector. It will be called R minus, it will be called R plus, and the resultant of this will be R plus minus R minus, and it will be called, here it will be two equal and opposite forces exerted a pure rotational force. What will be? It will be called as a force couple. Can you guess any example? Yes, if when you are driving your vehicle wheel, steering wheel, you are generating couples while rotating it. A very simple example. More examples will come. Let's see. How you calculate it? M is equals to R plus cross F plus R minus cross minus F. Here it is, R plus cross F and R minus cross F minus. Okay, so you will get an example of this is, since F and minus F are basically the same vectors, the force vectors F, we take it as a common into cross F, and this will be R plus minus R minus cross F. Of course, the vector R plus R minus is just the vector from the point where minus Fx to point where Fx. Okay. So the moment induced by two equal and opposite forces is equal to the moment of one force about the point of action of another. It does not matter which force you use to do this calculation. Okay, so it does not matter. You take the calculation from R plus cross F, the result will be, the moment will be the same, the couple will be the same, or R minus cross minus F. So remember, the answer will be still the same. Note that, very important, the force couple has a zero resultant force, and number two, exerts the same resultant moment about all points. Its effect is to induce rotation without the translation. So the effect of force couple can therefore be characterized by a single vector moment M. The physical significance of M is equivalent to the physical significance of the moment of the force about same point, as explained in the figure. Direction of M specifies the axis associated with the rotational act, whether it's a clockwise or anti-clockwise. There are practical examples of force systems that are best thought of as force couple systems. They include, now these are practical examples that will explain your concept further. The force exerted by your hand on a screwdriver. Very simple example. You do it a lot in your real world scenarios. The force exerted by the tip of a screwdriver on the hand of a screw. Very common example. The force exerted by one part of a constant velocity joint on another. Okay, these constant velocity joints if you see a bus or if you see a truck, you will see below there is a propeller shaft which powers the rear wheels. So those joints in which the propeller and the prop shafts are being connected by means of constant velocity joints. Then another example is a drag force acting on a spinning propeller. Okay, these spinning propellers, best example is you can see on the Fokker planes. Okay, then submarines, if you look at the rear of the submarines, there is a rudder. Okay, it also creates a drag force. Okay, then again we go ahead. Pure moments, couples and torques. Okay, so definition, physical interpretation and example. A pure moment is a rotational force. Its effect is to induce rotation without translation, just like a force couple. So example differentiating is the pure moment and the force couple. Couple and torques are other names for a pure moment. A pure moment is a vector quantity. It has a magnitude and direction. The physical significance of the magnitude and direction of a pure moment are completely equivalent to the moment associated with a force coupled system. So direction of a moment indicates the axis associated with its rotational force. The right hand screw rotation gives the direction. The magnitude represents the intensity of force. A moment is often denoted by a symbol. Again, very important, I ask in the exam to show the moment in a 2D symbol. How would you represent a moment as a 2D symbol? You will always give this example. If I ask you to show moment when it comes to 3D systems, and you have to give this example, and this symbol will be a 3D moment and this symbol will be a 2D moment. Okay, just go ahead and see further examples are there. Units and typical magnitudes of moment. In SI systems, moments have units of Newton meter. Why? Moment is force into distance, so Newton into meter. In the US system, moments have units of feet pound, foot and pound. The conversion factors of 1 Newton meter to feet pound is 1 Newton meter is equals to 0.738 feet pounds or 1 feet pound. Vice versa, if you go, it is equals to inverse of that equals to 1.356 Newton meter. Okay. Typical magnitudes are max torque exerted by a small Lego motor. For example, if you say build Lego blocks or Lego structures, Lego components, just to tell you, guide you, its magnitude will be equal to 0.1 Newton meter. Typical torque outputs of a car engine. So your car, when you start your car, you crank your car, you put your keys into the key holder and you turn it for the engine to start. That engine gives some sort of a torque. That torque's approximate magnitude to run that engine, when the engine starts and the main output, torque output is given at the wheels, and the result is that the wheel starts to rotate. Okay, so that approximate torque is sometimes in the range between 300 to 600 Newton meter. Okay. Like if you have got sports cars or Ferrari or basically Grand Prix, F1 Grand Prix cars, they will have very high torque. Braking torque of a human femur, this is if you accidentally you fell down and your human femur bone breaks. So it needs, in order to break that bone, a torque of 140 Newton meter has to be applied by means of any force on which you fell on the ground, and that force torque is somewhere in the range of 140 Newton meter. So if you go above that range, you are rest assured, unfortunately, your human femur bone is broken. If you are less than that, you are a lucky guy or girl that bone is not going to be broken. Another very important topic about movements is, just as you buy a force transducer to measure force, you can buy a force transducer. And remember, what is a force transducer? It is a more accurate, sophisticated device to measure the force, okay, by a force transducer that measure movements also. So there are some force transducers also which can measure movements also. We show an example of a force transducer attached to the wheel of a car during earlier discussion, okay. But precisely the exact device that measures the force is basically called as a torque wrench, okay. So this is often this is a device to measure the torque directly by just applying it on your bolt or on your nut. You will get directly the torque in terms of Newton meter or pound feet. So when you tighten the bolt on a precise machine, it is important to torque them correctly. For example, if it is a very hi-fi equipment where human life is involved, then you do not need to tighten your bolt or nuts by means of very simple or crude devices, but there you need this device torque wrench because human life is involved and they will give you the exact torque of those bolts. Okay, so if you apply too much torque, you will strip the threads will be failed and the bolt or nut will get loosened up. Okay, and if you don't apply enough, there will be a lot of vibrations in those systems, and those nuts can basically at high speeds can get loosened up and it can get off from the head of the body of the bolt head. Okay, the bolt will loosen it up, it will lose during the service. So that can be catastrophic if human life is involved. So how that device is looked, here is a device which is a wrench, but it is an electronic torque wrench. What does it do? Just apply it to your bolt or application wherever you are applying the torque, and it will give you here there is a digital space, digital output. You will get the torque over here, and so this is an electronic torque wrench. Just remember it in your future endeavors. When you go to the industry, you can see it, specifically speaking, the automotive industry or space industry, or if you go to Sparco or other hi-fi or Camera, PF based Camera, where your JF-17 Thunders are being made. So where they, if they are tightening any bolts or aluminum bolts or they will basically be using by means of this electronic torque wrench to apply the correct torque. Then we go, very important slide is over here, engineering systems that exert torques. There are many practical examples of movements or torques in engineering systems. So just read one by one. I can ask you in your exam in a different way, in your quiz, in your MCQ. The driving axle on your car turns the wheel by exerting a movement on them. Okay. The drive shaft of any motor. In your home, if you look, you have got your water pump or your motor, which basically sucks the motor and sends you at your higher story buildings. So the drive shaft of any motor exerts a torque on whatever it is connected to. In fact, motors are usually rated by their torque capacity. So if you go to any place or to buy your motors, you will always be telling them the torque capacity of your motor, and then you will buy it in the industry. So this is new knowledge for you, that when you buy, you will be basically telling them their torque capacity. The purpose of the gearbox is to amplify or attenuate torque. Gearbox, where it is placed, this gearbox is usually being placed in your vehicle, in your motorcycle. There is a gearbox. So you apply a torque to the input shaft and get a bigger or smaller torque from the output shaft, depending upon the gearbox. You remember, if you drive your car, you've got various gear 1, gear 2, gear 3, gear 4. You apply the most speedy gear is the 4th gear or the 5th gear of your vehicle, and the gear in which your car goes very slow is the 1st gear. Okay, so you apply a torque to the input shaft and gets a bigger or smaller torque from the output shaft. To do this, the input and output shaft have to rotate at different speeds. Okay. A torque converter, a very important device. serves a similar purpose to a gearbox. Okay, movements are also applied as reaction forces. Okay, so movements are not always live movements, they can also be considered and calculated in statics and in dynamics as reaction forces. Okay, for example, if you see a person diving in a swimming pool and he is diving on a diving board, it is always fixed at one side, and the other side the diver basically makes many jumps before diving into the swimming pool. So you can easily calculate the movement of this fixed board or a fixed beam which is fixed from one side and free from the other. So on the fixed side you can calculate the moments. Those moments will be called as the reaction forces. The resistance you feel to turning the steering wheel of your car is caused by the movement acting on the wheel. Another example where they are touch the ground. The rolling resistance you feel when you ride your bike over soft ground or grass is also due to movements acting when the wheel touches the ground. Movements appear as internal forces in structural members or components. Okay, so they appears as internal forces in structural. Whenever we go for structural analysis, we will consider movement as internal forces, which means if we cut it at any point in our beam, we will be able to calculate those movements as internal forces. For example, a beam will bend because of an internal movement whose direction is transverse to the direction of the beam. Again, this is a bit more theoretical. Just read it. When the chapter will come, especially the chapter 5 and 6, we will be applying this theory. So just you need to read it a little bit. If it doesn't understand, no problem. The practical numericals are coming. It will basically further elaborate your concept. But when you have read this a bit, you will have a little bit knowledge. And when your little bit knowledge, you will apply to the practical concepts. Your basically understanding and your visualization will help you enhance your conceptual theories of statics and dynamics. So that is why I am trying to tell you. Just as an internal force causes points in a solid to move relative to each other, and internal movement causes to rotate relative to each other. Okay, so this is another example. So I think we have reached the end of it. So these three different in this video I have shown you three different slides. So this basically gives you the overall theoretical concept of statics, because statics is altogether related to force and moments. So if you understand force and if you understand moments of this, what you have told in depth, this is an in-depth explanation with some pictures, some figures, some practical examples, some practical real world examples I have shown you, I have told you, to understand the concepts of forces and the concept of force movements, the concept of couples and the force couples and torques. So this basically gives you a theoretical knowledge. So after attaining this knowledge, now we will basically go to the real world picture of how movements are being applied to real world systems, and then we will basically be going to understand the numerical aspect of this chapter movement. Because remember, if you do not understand force correctly, you will not be able to understand movements correctly, and if you do not understand the chapter of movements correctly, you will definitely be in basically big trouble in when we go to the chapter 5, and when we will go to chapter 6, there we will basically be dealing with real world structural systems. We will be dealing with real world frames and we'll be dealing with real world structures which is called as machines, like your engine is a machine. Then from the petroleum point of view, you've got what is called as an oil rig, a derrick which is being placed on and an oil rig is over there which is continuously reciprocating and oil is being sucked out. Then you've got horizontal rigs, you've got drilling, you've got vertical drilling, basically then there is offshore drilling over there. So these are all very complex machine systems. So and how they are running, basically there are a lot of various types of forces, movements, motors, torques being applied, and the output is what that they are basically sucking from the ground the crude oil and that crude oil is basically going to the refinery. So these systems, if you don't understand how they are being built and how they are being forces are being applied, working is very important for especially petroleum engineers. Okay, so this you need to understand what in my slides I have told you, and if there is anything complex that I have not told you, just because just for you I am not going in that in-depth detail of that theory. So just giving you a little bit knowledge over here of the theoretical aspects and a little bit practical aspects. Now we will basically be going to start our chapter of moments. Okay, so now let's see, we start this chapter. Okay, system of forces and movements. Okay, chapter 4. So what do you see here? The effect of force can depend not only, this is a very real world and practical system. So the effect of force depend not only on their magnitudes and directions, but also on the movements or torques they exert. The rotation of an object such as the wheels of a vehicle, crankshaft of an engine, and the rotor of an electrical generator resulting from the movements of the force exerted on them. So if an object is in equilibrium, the movement about any point due to the forces acting on the object is zero before continuing on this. Okay, now this all thing theories over here they have explained you in the, but I think you will be able to understand very quickly, very easily, and as your database of theoretical knowledge of force and movement, I have already widened it up. So all this theory you can understand it yourself. So now see this picture. Okay, so there is some sort of a crane is being there. It is being fixed on some sort of a horizontal, vertical derrick or the vertical frame or a column of trusses is being placed. And here, if you look at it, it's a horizontal structure of a crane which is being fixed by means of some ropes or cable system over there. And then there is basically some weight is being placed at the end. So if you look at it, this is some sort of a perpendicular distance, okay, and then this is some sort of a weight which can be treated as a force. So what is the result here you see is weight or force and perpendicular distance over there, and this is basically what is being generated. This is a movement is being generated over here. So the counterweight, where is the counterweight? This is the counterweight of the building, creates a large amount of what? A movement. What is that movement? Weight into this distance that the crane structure must support during assembly. In this chapter, basically we calculate the movement of the force and analyze the system of forces and the movement. Okay, so what is he trying to tell you in this chapter is basically this structure. The counterweight, where is the counterweight? This is the counterweight which is basically being balancing this movement effect over here. And what you see over here is basically a cable is being attached over there, and this cable is further, if you look at it, we go previously, this cable over here, if you look at it, it is basically supporting this movement effect of this weight. If we break this cable, if this cable is being broken up, then the movement might be generated as so much that this structure can basically, if you look at it, it can fail from where it is being fixed. So it can, a failure can result over here. So another thing, if you look at this picture, there are these people over here, 1 person, 2 person, 3, 4 persons, another person might be over here. So since the moment generated magnitude is so much, we will not be considering the effect of these persons which are standing on the crane deck over here. Okay. So another thing over here is, if you look at it on the right side, there is this vertical force is being applied, and then there is another round thing. Remember, in 2 dimension, what is this round thing is called? In the previous knowledge of movements I have given you, what is this? This is an example of another movement. Okay, but this movement over here is basically telling you that this is not the movement of generated because of this vertical force and this distance, but this is another movement being generated because of the reaction forces of this vertical force. Again, if you look at it very clearly, if you fix over here, this force and this perpendicular distance will basically be taking this crane deck in which direction of the clock? If you look at it, it will be taking it in the anti-clockwise direction. It will be taking it in the anti-clockwise direction. But if you look at it, this moment, it is being fixed, this deck is being fixed over here, and because it is fixed, it will give a reaction. And see why this reaction is in red. Why? Because it is a movement. Okay, it is a movement reaction, and this movement reaction, because you want your deck to be in equilibrium, so one movement will be generated because of this force into perpendicular distance, but there has to be an, if there is this not movement over there, this movement is not there, this horizontal deck will start to rotate in the anti-clockwise direction. But you want your system to be in equilibrium, so that equilibrium is being provided by this, where does it go, provided by this red movement, which has to be totally in equilibrium. It has to have the same magnitude, but the direction provided by this will be opposite to this one. So you must remember this point very clearly, because this, when we go to another chapter, this point will come. So we will this red rotation movement and the vertical force which is lying on this movement is again very important, because the system has to be in equilibrium. So this force of this counterweight, say this is say 500 pounds, so another force has to be generated which is also 500 pounds, because the system, I told you, has to be in equilibrium, remember. So these two forces must basically try to cancel out its effects. So now you apply sigma, say if it is 500 pounds and this is apply 500, apply sigma Fy, so you will say this Fy will be negative and this Fy will be positive. You add those two forces, your system will be in equilibrium, plus 500 minus 500. Now what about this one? Say this again, say this is force times perpendicular distance generated a moment of 200 Newton meter. Yeah, or say it applies a moment of 200 pound feet, say for example. So this counter moment must also be equals to be of 200 pound feet, but this 200 pound feet will be anti-clockwise and it will be taken as positive, and this 200 pound feet which is clockwise, it will be taken as negative. So you apply summation of moments over here, this will be positive 200 pound feet and this will be minus 200 pound feet. You add them and what is the result? You will be surprised, it will be 0. And you apply those vertical forces and you see the result again, 500 pounds minus 500 pounds, and the result is again 0. So it means that when you apply sigma F and you apply sigma M, the net result is 0. And what does it means? It means that this crane will not move. There will be no motion in this crane, and you are standing say 1000 feet above the ground. So you don't want this crane to flutter around and move around or translate or rotate around. You want it to be static, otherwise your life will be in jeopardy. So this is how you calculate the moments and forces. Okay, so this is a very good example that I wanted to show you, and just to enhance your concepts. If you understand these concepts, when we go ahead, you will see that this is very much an easy topic. Just a basic fundamental knowledge of force and moments will help you understand the numericals better. So I think when we go ahead, you will be able to solve and understand the numericals very easily. So we basically, I think, stop here for the next class. Okay, we stop here.